for the antifreeze lab, the first step is going to be preparing solution 1. Solution 1 is made of ethylene glycol combined with some water. So what I'm going to do is, first of all, I'm going to measure out the ethylene glycol. Let me just use this clean, dry beaker. Okay, I'm going to tare it, of course. And we're measuring it out in grams, which is unusual for a liquid. A lot of times liquids we would measure in terms of milliliters, but in this case I want to know the grams. So let's see. 4. Looking for 5 grams, as close as we can get. Very close. 5.01, that's pretty close. Maybe I can siphon out. I need it. Put some of it back. Still a little too much back. 5.01, I'm just trying to get it right on the 5.0. 5.01 would be fine, by the way. There we go, 5.00 grams of ethylene glycol. Then what I'm going to do is I'm going to add 50 milliliters of distilled water that I've measured out before. This is not tap water, this is just regular distilled water. And I'm just going to pour that in there, making a solution. Remember, a solution has 2 parts. It has a solute and a solvent. I think it's pretty obvious which one is the solute and which one is the solvent. Remember, I had that little bit, like a few of these micropipettes full of the ethylene glycol, and then I put in 50 milliliters of distilled water. This is my solution number 1. I'm going to put it right here. Solution number 1 has some ethylene glycol mixed with water. Solution number 2, okay, again, I want to tare this. Notice it's just slightly different than the mass of that other one. Every beaker can be slightly different in mass. And I'm also going to add the green one. Okay, same one. Notice I'm not using the pink one. Let me explain that in a moment. And I'm going to try, but let me pour a little in this time. So we can get up closer. Get up closer. We know about how much it's going to look like now that we've done one. Putting in twice as much. So I'm going to try to get it right on the 10. Right on the 10. Let's see how close we can get. And 4. 10. Boom. So 10 grams of ethylene glycol, and this is my solution 2, as twice as much, but I'm going to put in the same amount of distilled water, and let me pour it in. That actually does a really good job mixing it. If you pour it in fast, it just kind of mixes it up as you pour. And so now I've got solution 1 and solution 2. Solution 1 and solution 2, I'm going to measure their freezing points. And I'm going to compare it to just the regular old distilled water when that freezes. And we're going to find out the delta T. The delta T is the freezing point depression. And using that, we're going to calculate the molality of the solution. Okay, using just the delta T, just the temperature on a thermometer, we're going to be able to tell this number, the concentration of a solution in molality. Okay, now let's talk about ice. Ice is a kind of perfection. Ice is what water wants to do. Water can make ice if it just chills out. Okay, all it has to do is literally get colder, and then it organizes itself into this beautiful, beautiful structure. The structure inside of an ice cube is really just sheer perfection. Okay, it's very similar to the structure inside of a diamond. It's hard to show that with this particular model, but it's very similar to that perfect structure inside of a diamond. Okay, but then wait a second. Sometimes we mess that up because we put an obstacle in, like ethylene glycol. An obstacle to the water freezing. Well, that obstacle makes it a little harder for the water to freeze. Okay, when the water tries to freeze, okay, I skipped one here. Okay, now they got to freeze around. Now they got to freeze around those obstacles, making it a lot harder and pushing down the freezing point. The word depression literally means push down. So now I'm going to prepare my ice baths, And what I'm going to do is I'm going to scoop up just some ice, okay? Just a whole bunch of ice, filling it up most of the way. I got to leave enough room so that I can fit those, test tubes in here. I can fit the test tubes down in there, okay? And then, well, that's not cold enough because that's not going to freeze this. I need to make it colder. I'm going to use the trick that they use for making ice cream. I'm zeroing that. I'm going to add about, this doesn't have to be as exact, I'm going to add about 20 grams. That's a little more. Let me get those ones off the balance. Add about 20 grams of sodium chloride. 23, over it, 22, 21, that's close enough, about 20 grams. So I'm going to sprinkle that. I don't want to get it in my ethylene glycol. I'm going to sprinkle that on my ice, and then I'm going to try to get it distributed around in there. I might have to sort of stir it around a little bit to get it to contact all the ice cubes. And then what I'm going to do is I'm going to put a little bit of aluminum foil around it just to slow the transfer of heat a little bit to the outside world. Now, the aluminum foil itself doesn't do a great job of that. Okay, it's actually a conductor of heat, but it makes a little pocket just inside it, and that pocket really, really slows the transmission of the heat. So that's one of my ice baths. I'm actually going to prepare 3 of these just because I'm going to do them all simultaneously. Usually when students do this lab, they just make 1 ice bath, okay? Now remember, by the way, let's check the temperature of ice. It's probably about what you think it is. Let's see, the temperature of ice on its own. I'm going to use this digital thermometer to measure my ice bath. It's getting down to 1 degree Celsius, 0.9, 0.7. It's dropping, it's approaching 0. So we would expect the ice cubes to be around 0. Now it says negative 0.6, so it's a little bit below 0, okay, for this ice bath. But that's not cold enough. I'm going to, again, add about 20. Let me see, what did 20 look like there? It wasn't that many scoops, really. Oop, that wasn't 0, was it? Always remember to 0 your balance and to make sure you get the right amount. And it doesn't have to be exact here, but we want around 20 grams of sodium chloride. So what the sodium chloride does is it gets inside, the ice cubes start ripping it apart and they get even colder. It actually absorbs energy to rip sodium chloride apart. That's close enough. It actually absorbs energy to rip the sodium chloride apart, so it makes the ice even colder than it is right now. So if I mix that around, if I get that a little bit mixed up in there, this is the trick that ice cream makers use to get a temperature that's well below freezing, because some dairy products don't freeze at the freezing point of water. You need to get them colder. Okay, and again, I'm going to put the aluminum foil around it for the same reason. And this is my second ice bath. Okay, it's going to get very cold. Okay, and then I'm going to make 1 more, same way. Okay, same way. I'm going to scoop up some ice, a whole bunch of ice. So as much as I can fit in there would leave a little bit of room for a test tube, of course. And then I'm going to measure out my sodium chloride and I'm going to tare it. Tare and 0 are essentially the same thing. Put in approximately 20. This isn't undergoing the exact chemical reaction we're measuring, which is why I'm not being as accurate. 21 is close enough. Pour it in there. Again, careful not to get it in my ethylene glycol. That can really change everything. If you get it into your ethylene glycol, it can actually change this entire experiment. Then I'm going to mix it up. And then I'm going to get the aluminum foil to put around it. And these are my 3 ice baths. So now we're going to measure how cold they get. They need to get really cold. How cold they get? Well, it has to be at least, let's say, negative 8 Celsius. Well below freezing for this to do a good job. And I'm going to use my digital thermometer to measure it. Let's see, maybe stir this one around a little bit more. poke it around a little bit more. I'm going to use these stirring rods for stirring, not the thermometers, because thermometers are hollow on the inside. They can actually break pretty easily. And I'm only going to use my digital thermometer to measure the temperature of the ice bath. And I'm going to use my other thermometers exclusively for going into the test tubes. So now I'm going to prepare my test tubes of my solutions. The first solution is just actually going to contain water. And the amounts I'm going to put in, each one are going to be the same amount. I'm going to measure out 5 milliliters of each one. I'm going to measure out 5 milliliters for each of these different solutions. So for the water, let me measure about 5 milliliters and pour it very carefully, slowly. Get it up to the 5, just over the 5. And let me take a little bit out with this pipette. And let me see, let me double check, let me look at it eye level. If it's on the 5, I went a little bit under. Let me kind of drop back. Okay, that's good. That's right on the 5. So this is now going to be my test tube of water. I'm going to pour that in. It's not very much. It doesn't look like much in a test tube. And we're going to use that as our control. Like, when does the solvent freeze? When it's pure. Now notice that this ice bath is now at negative 16 degrees Celsius. And we are going to put this test tube in it. I don't want to break the test tube. So I have to sort of ice break a path in there. Ice break a path through the ice. Get it down deep near the bottom, surrounded by that ice, but not necessarily touching the bottom. There we go. I think I got it pretty down deep. Yeah, there we go. And then I don't want to use this thermometer, which has contacted the salt, to measure my freezing point. I'm going to be using another thermometer. And I guess I can just sit that in there for now, but when I'm measuring it, I want to pull it off the bottom. Okay? So that's my water. For solution 1, I'm also going to measure out 5 milliliters. 5 milliliters of solution 1. Because if I tried to freeze this whole thing, it would take a long time. It would freeze at the same temperature, but it would take a lot longer. So I don't want to wait that long. I want to just fill this up very carefully to 5 milliliters. 5 milliliters. And let me make sure that it's right. Here. Yes, that's 5 milliliters. And I'm going to pour that into a second test tube. This is solution 1. This one looks pretty clean. Got that nice clean test tube. Pour that in. So notice, that's not very much. 5 milliliters of solution 1. 5 milliliters of solution 1. But it'll freeze at the same temperature that would. It'll just happen a lot faster. So again, I'm going to ice break my way through this. Ice break my way through this. This is probably at about the same temperature as the other one is. Okay? And we're going to see when this freezes. Okay, we're going to use another thermometer for that one. And of course, I'm going to be pulling it off the bottom when I'm measuring the freezing temperature. This ice bath is probably about the same. I'll check that while I'm preparing the third one. Okay, the third one, I'm going to take 5 milliliters of solution 2. Okay, 5 milliliters of solution 2. I'm going to put that in there. I'm going to put that in there. And I'm right below the 5. Just one more drop. Okay, that's right on the 5. So that's 5 milliliters of solution 2. I'm going to pour it in a clean test tube, clean dry test tube, and we'll see what temperature that freezes. So in other words, we're going to see how much the freezing point is depressed, is pushed down, by having added the different amounts of ethylene glycol. Remember, there we go, nice and low. Okay. And I'm going to use another thermometer again to measure the temperature of that. So now notice that in this solution, well, this was not a solution, this was just pure water. And then in this solution I added a certain amount of ethylene glycol. Okay? In this solution I added twice as much. So we expect the freezing point for these two to be different, and we'll see how much the ethylene glycol pushes down the freezing point. This one is at negative 10 degrees Celsius, so what I might want to do is actually stir it around a little more, get the sodium chloride more distributed, to make sure it's nice and cold. And then I want to make sure not to break the bottom of my test tube. And then for this one, I want to check the temperature of the ice bath, and I might have to do that as well if it's not cold enough. If the temperature, I want to have a nice cold temperature, like at least like -8 would be a good temperature for that. Okay, so we'll come back and look at what temperatures they freeze at in a little bit. Okay, so now we're going to check if any of these are freezing. This is the distilled water, solution 1, solution 2. I moved them over here, and the ice bath is nice and cold. It's about -10. And let's see, do we see, oh, I do see some ice. Look, see the ice forming inside of the distilled water. So what I want to do is pull this off the bottom, and you can see that it's right on the 0. Boom, it's right on the 0. Now you might imagine that I would put it back in and let it keep freezing, the rest of that ice freezing. Okay, but I don't want to, because it'll make a popsicle in there, it'll make an ice cube inside there, and it'll break the test tube. So now I'm going to leave it in here to cool off and thaw. Okay, and let's check if this ice bath is cold. This ice bath is nice and cold. It's also -10. Let's see if this one is freezing. Oh wait, yeah, it is. Wow, already. Okay, solution 1 is freezing, and even while it is freezing, that's a good enough temperature. We don't want to make a popsicle again, and I don't know if you can see the slushiness that it's making on the bottom. Okay, so let me get a good temperature. It'll stay at its freezing point until it's frozen. I'm getting negative, it's below 0, 3 point, it's almost between the 3 and the 3.5. I would almost want to say 3.25 if I could call it, but these readings aren't usually that accurate to get it to the 3.25. I'm going to say -3. If I had to call it, I'd just say -3. It's closer to -3 than -3.5. So that's the temperature of that one. Well, that was good. That happened really quickly because I got a nice cold ice bath. And again, I want to let that thaw, solution 1. So solution 2, let's see if it's ready. Maybe, okay, the ice bath maybe is cold enough. Ooh, it looks like the ice bath might not be cold enough. I might have to adjust this ice bath. So let me see if it's freezing yet. Actually, oh, it is. It is already freezing. Wow, that's great. And the temperature that this is freezing, let me see. Let me get it off the bottom here, off the bottom. And it looks like just beyond -5. Again, it's just like between the -5 and the -5.5. Give it a second to adjust. Ooh, I'd almost want to call that -5.2, something like that. But because we have to round it, oh, you know what? It is going closer. I'm going to say -5.5. -5.5 for the freezing point for solution 2. And that happened really quickly. I guess I had nice cold ice baths. And you might wonder, why do I have this pink one here if I didn't use it? Well, that's because we usually use 2 different kinds of ethylene glycol in this lab. We usually use the green version and the pink version. Well, actually, they're pretty much the same chemical. Pretty much they're the same, except for they have different additives. Okay, the additives actually will change the conductivity, even though ethylene glycol is what we call a non-electrolyte. Well, let's see if this particular solution lights up the conductivity indicator. Let me see if I can get a good reading here. Got to get it near the edge. Oops, I poured it in there. And do I get a good reading? Usually it lights it up. Let's see. Okay, let me just dip it directly in there. We usually try to avoid that. See that lighting it up? Okay. So the ethylene glycol is not an electrolyte, however, the additives are, so it makes it light up. So it gives you a false positive. We call that a false positive. Let's check this one. So both the green and the pink stuff light up the conductivity indicator, and that's because of the additives, the things that make it green and the things that make it pink. Okay? So basically, now we have our measurements. We have the freezing point of just the distilled water, and then we have the freezing point of solution 1, okay, which of course was depressed. Then we have the freezing point of solution 2. Notice how it's darker green. Okay, it was pushed down even more. So the freezing point depression is the pushing down of the freezing point of the solvent based on how much of the solute is added. And then using this calculation, we can actually easily solve for molality. Okay, molality, which actually is something that will reveal how many moles you have. If you know how many moles, you can figure out the molar mass. So the calculations for this lab, are a little bit tricky, but the simple one is this. You find the delta T by checking how much the freezing point was pushed down, how much it went below the original freezing point for just the pure solvent, which was the distilled water.